Hello, everybody. In this week's QTFMS seminar, we're hosting Thomas Van Riet from KU Leuven, and he is going to talk about the status of scale separation. So, Thomas, thank you for accepting our invitation. So, the
Yeah.
stage is yours.
Okay, my pleasure. And hello, everyone. So I realized when I said yes to this talk, I realized a bit later that recently my collaborator, Nicolo Cribiori, had been talking about something very similar. So when I realized it, I decided to do something which is a little bit more colloquium style. And only the last part is more about the current research. So it's more about the motivation, and I hope you find it useful. And yeah, I strongly invite you to ask questions because especially if they're also master students, it might be a little bit too, how do you say, too advanced. So feel free to ask any question. Okay, I'm happy to answer them. Um, so most of what I'm going to say, of at least the sort of the big picture things, can be found in lecture notes that I wrote together with Gianluca Zoccarato. I think they're now 3 years old. And they are targeted at, say, master students level. So you don't need to know actually string theory really to be able to digest those lecture notes, including the exercises. Still, you get, I think, a good glimpse of some of the state-of-the-art topics on the swampland. Okay. All right, so let me start with some general words about extra dimensions and string theory. So I would say that string theory revived a little bit the old idea of unifying forces in the way of Kaluza and Klein. And it does so in a bit of a novel way, in the sense that if you string theory enforces a certain number of space dimensions upon you, and I think this is very healthy in the sense that any fundamental theory of nature should also tell you what is the space-time dimensionality. As some people say, it's very off in string theory because it's typically 10D. But this is, of course, a non-trivial statement to make, right? Exactly because dimensions can be small. And it's often said that if dimensions is small, it's very ad hoc. It's a way to hide your problems, to put them under the carpet. And I want to argue this is very much not the case in this talk, okay? So in general, I want to start with some criticism on string theory and to address it. And the reason I want to do that is that if these days you Google something about string theory, say that you're a beginning physics student, and you're deciding what directions to take, and you Google, for some reason in the last 4 or 5 years, the thing that dominates the internet is discussions about string theory. Is it making sense? Is it physics? And I think that's very unfortunate that the controversy took over the science. And so that's why I want to address it, because there's a lot of words and people don't say the easiest things. Like usually people complain about experimental verification. And I want to say that's a valid criticism, but you should know this applies to everybody who will ever discuss physics beyond the standard model. Right? And this is simply a fact of life, of quantum field theory, that the Planck mass is high. So any quantum gravity effect is typically suppressed by the Planck mass. And so it's very, very hard to detect. Okay? And you need to go to high energies. This will be true for anybody out there who will claim to have a theory of quantum gravity. Yeah. And I think, in fact, that string theory, interestingly, typically puts the fundamental scale at lower energies than Planck scale. So it's in that sense even doing better with respect to what you naively would expect. Secondly, a typical other topic of complaint is that string theory comes with a landscape of ground states, which we call vacua. And I want to say that, in fact, the history of physics is exactly such that the more fundamental a theory became, the more simple the equations of a theory become, the more complicated the vacuum structure. Especially if you think about nuclear forces, if you think of the history, it started out with huge Lagrangians, huge Hamiltonians, And then people realized it was all based on symmetry, became much simpler. And in the end, if you think at least of pure QCD, the Lagrangian couldn't be simpler, right? This is it. And I just want to give this example because it shows something very fundamental. That, you know, it's very simple. And then you go to the vacuum structure and it actually starts becoming a little bit complicated, right? As people realized, you know, a field strength can be locally zero, but it can have a non-trivial winding number at infinity. So then you realize, for instance, for pure QCD without even matter, that there's an infinite amount of possible ground states. And a little bit like, you know, the harmonic oscillator, like say the double well potential, we know that quantum mechanics can lift a degeneracy, right? But if you studied quantum mechanically this classical degeneracy, maybe you've heard of this, then the vacuum structure of QCD still has a degeneracy. And it's a degeneracy which turns, say, if you like, a classical discrete infinity into a continuous infinity on the circle. So it turns out that the natural quantum states are what we call theta vacua. And they're like specific superpositions of these winding gauge field states, right? And with gravity, things can even complicate a bit further compared to this picture. But I think this picture already in Yang-Mills theory captures a lot of sort of the discussions about vacuum degeneracy in string theory. But so let me quickly explain that in gravity for you, right? So let's do the same for gravity. So let me take pure Einstein equations, no matter. Just like I had pure QCD, no fermions. And then we all know that, okay, what kind of solution solves the Einstein equations? Well, the solution with the most amount of symmetry is just what we sometimes call flat space. Minus dt squared plus dx squared plus dy squared plus dz squared. So you'd say, well, that's a unique vacuum. It's actually not true. This is an infinite amount of vacua. And one way to see that is that, you know, Einstein's equations or Einstein's expressions are blind to topology. Yes, this can be the metric on 4D Minkowski space, but it doesn't have to be the metric on 4D Minkowski space. A trivial example is that I can decide to periodically identify the coordinate x. I can say x equals x plus 1 centimeter, but I can also say x equals x plus 2 centimeters. All of that are proper vacuum solutions, right? And the difference between Minkowski space and this one where I identify x, it's a topological issue. Just like with Yang-Mills theory, which had different gauge field windings at infinity, yeah? And so there's much more than this identification. If you want to know, you want to Google it. All the possible Riemann flat metrics, they're called the Bieberbach classification of Riemann flat manifolds. There's a huge amount, okay, with a hugely complicated topology. So we already learned that pure Einstein's theory, classically, like Yang-Mills theory, has a very complicated structure of vacua. Yeah. And of course, you know, our universe, nobody lives in a vacuum, because if we would, nothing would happen. All of what we observe is an excitation upon a vacuum, right? So if we, you know, remove galaxies, dark matter, radiation, black holes, we would say we have a flat universe if I'm ignoring dark energy. But you could say, well, I actually know in that case what vacuum we are. And I'm also saying, no, we don't. I don't think we know that it's Minkowski space. It's perfectly consistent with current day cosmological observations that the spatial topology of the universe is, for instance, periodic. The spatial topology of the universe could be completely a 3 torus. We don't know. The only thing we know, if the topology is non-trivial, it has to be non-trivial at the order of a length scale of the visible universe, so what you would call the Hubble scale. So it has to be, you know, the periodic dimensions have to be huge, but it can be very natural. Imagine the universe, you know, you go back in time near the Big Bang, you know, spatial dimensions could have been small circles who have been blown up to very large circles. We wouldn't see that today, okay? It's perfectly consistent. So that's classically. So what happens quantum mechanically, right? I showed you for QCD, quantum mechanically, you have a discrete infinity is turned into a continuous infinity on the circle. And quantum mechanically, what happens in gravity is less trivial. So we know for sure that quantum effects tend to generate a potential for L. I'm just doing the simplest example where I decided to periodically identify X, right? But there are many numbers L, if I do all this Bieberbach classification. And so quantum mechanics tends to lift this continuous degeneracy, because for any real number L, I had a solution to Einstein's equations. But it does so obviously at what we call small length scales, right? You can imagine that quantum mechanics is not important at big length scales. Indeed, if there's something like called a Casimir effect, it is only sort of measurable and big when L is small enough, okay? And so this, was well understood. And I think what is a very interesting paper about this, which I think somehow is not sufficiently well known, is this paper by Nimar Kanihamet and collaborators from 2007, who observed that if you just take the standard model as we know it, and we couple it to gravity, there's a huge landscape of possible ground states. And in fact, most of the vacua of the standard model to an observer would appear to be one-dimensional, two-dimensional, or three-dimensional. And the number of four-dimensional vacua, the ones we are clearly observing, is much, much smaller group. Okay? So bottom line, the standard model has a huge landscape of vacua, of ground states, especially when you couple it to gravity. So if somebody comes with what we call a UV completion of the standard model coupled to gravity, aka a quantum gravity theory, I hope it's a theory with a landscape, because if it doesn't have a landscape, it's just an inconsistent theory to begin with. Okay, so I hope that addresses a little bit some of the criticism that you often hear. So in this regard, I told you that I ignored dark energy. Let me now not ignore dark energy anymore. Okay, let me think about dark energy. And let me think about what we call the cosmic hierarchy problem. And I think it's a complicated problem. And I think if you read about it, you can see it's complicated because everybody has a different way of explaining it. And so I think the best way of explaining it or giving a flavor of it is by thinking in terms of what we call it Wilsonian effective field theory, right? So it's where I think about what happens at different energy scales and how does it change the physics at observed low energies, right? So one thing that you might remember from your course on quantum field theory, if I have some scalar field with a mass m, and I just ask what is the expectation value of its energy density in the vacuum, then you see that there are many contributions, but it starts off with a loop vacuum diagram, which scales like, well, with the if you compute it, it goes like m to the power 4 times a log term, where this log term contains what we call the RG scale. But that's not so important. It's really, I'm talking about m to the 4th term, right? So it means that quantum fields, like bosons, they will contribute this amount to the vacuum energy. And then one way of explaining, I think the proper way of explaining what we call the cosmic constant problem is that you see that, in physics, we usually are ignorant about what happens at high energy scales, at scales that we haven't measured before. There can be a whole zoo of massive particles, right? The thing we notice is that all of these massive particles, they will contribute significantly to the vacuum energy. So if you want to say, okay, we live in a universe where we almost don't observe vacuum energy, it's like super tiny, 10 to the minus 120 in Planck units, then if somebody takes that theory and changes some of the tiny details of that theory at very high energies, which are anyhow the energies we're not observing, it would completely change the cosmological constant that is observed, right? So we say that, the real issue is what we sometimes call the UV sensitivity of vacuum energy, right? And in the language of effective field theory, it has to do with the fact that vacuum energy is a relevant operator of dimension 4. The other relevant operator in the standard model is a Higgs mass. It has dimension 2. And not surprisingly, the two relevant operators are the two that come with what we call naturalness problems, right? So for vacuum energy, we call this a cosmic hierarchy problem. And for the Higgs mass, we call this a weak hierarchy problem. Yeah? And these are the two big hierarchy problems in fundamental physics. And it's just telling us that the value of these two measurable parameters is fixed by the highest energy scales, okay, by the physics at super high energies, right? So I like a slide which I took from Aaron Wall, which I think captures the intuition. And this is the intuition I like to use. So what you see on this slide is some relevant parameter on the vertical axis, G0. So think of it as a Higgs mass or vacuum energy. And then the horizontal axis is energy scale. And so what you can try to do is you can try to fine tune, your Lagrangian such that at highest, high energy scales, you fine tune it very precisely so that if you flow it to low energies, that it becomes very small. But you see that the smallest change in the ultraviolet, you go 1 micromillimeter up or down, will make that, this relevant parameter either goes to very big positive values or very big negative values, right? So that's really the definition of the hierarchy problems. It's the UV sensitivity, okay? So, a natural value, what we call naturalness, roughly speaking, is to say, we don't do this fine tuning, right? Why would there be this fine tuning? But if you don't do that, well, the natural vacuum energy would be, famously this huge amount of energy in electron volts instead of the observed 0,001. Yeah. And so I think what we are learning is that it's very difficult to say something sensible about vacuum energy in quantum field theory. What you really need is a theory of all energy scales. So you need to have a UV complete description that includes quantum gravity, right? And so I think more importantly, what I think humanity is facing with these questions is sort of a lack of the decoupling principle in a way. Yeah. What I'm trying to say with this is that, if I'm an astronomer, if I'm a geologist, if I'm a biologist, I can work on my scientific field without having to know the smallest energy, the physics at the smallest energy scales, right? I mean, a biologist doesn't need to know about QCD. A geologist doesn't need to know about QCD. An astronomer, for sure doesn't need to know about quantum gravity. But suddenly, a cosmologist, that's a person who looks at, the biggest energy scales, biggest length scales in the universe, that person suddenly needs to know about subatomic physics. That is what the hierarchy problem is telling us. Yet another form of the rephrasing of the hierarchy problem, which is important for what I want to explain you, is to ask yourself the question, why is the observable universe so big? Right? That is, I think it's the same question. Because if vacuum energy would be big, imagine it's very big positive, right? So that means that there's a huge dark energy force, say of Planckian size, and it pushes all objects apart in the universe. Well, then atoms would not even exist. Electrons would be pushed out of an atom because of dark energy, right? And the observable universe would be a Planck scale. Why? If you would go 1 Planck distance away from your eyes where you observe, things are already moving away from you faster than the speed of light. So your observable universe would be like a Planckian size box. And we need to understand why the observable universe is so different. And the question I want to address is, is this a natural place to look at the physics of extra dimensions? And I think the answer is absolutely yes. The physics of extra dimensions is crucial in understanding this issue. Okay, so let me try to explain why that is the case. And if I go too fast, please interrupt me. If I'm saying too obvious things, you can also let me know. All right. So the great thing about string theory, whether you believe it's a theory of the real world or not, I think it's not so important. Think of it as a theory like the Ising model. It allows you to do computations. And I think it's amazing that we have a theory that includes gravity, where we can at least compute things like a cosmological constant, vacuum energy, because we don't have a cutoff. So we know how to do the calculation, right? So how do we do the calculation? Well, string theory in the most vanilla form has 10 space-time dimensions. And what we usually do is that we curl up 6 of them. And I think that verb curling up is very bad, but okay, I'm using it. And what we read off, we have a metric which has 2 length scales, right? There's a green part here, that's the observable universe. And it comes with a curvature scale. And that curvature scale tells us about the cosmological constant. And then the red guy here, that's a metric on the compact space. It has a finite size. And it has a different length scale associated to it. Okay? The length scale associated to the small guy, we call the Kaluza-Klein length scale. And one way of defining it is by just saying, well, it's like the 6th root of the volume. And once you have, in physics, a length scale, you can just invert it and it gives you a mass scale. And this mass scale is sort of the mass scale naturally associated with vibrations of these extra dimensions, right? So vibrations of these extra dimensions, to a 4D observer, they would look like particles with a typical mass scale given by this formula, m being the inverse of L. Okay?
Can I ask something?
Of course.
With the previous slide.
Yeah.
When you say the Kaluza-Klein mass scale, you're basically stating that there's a new physics arising at that scale, right?
Yes.
And we know that emergent string conjecture states that there are 2 Tauro states, actually, one being string and the other one being the Kaluza-Klein state.
Yes.
Why do we write directly Kaluza-Klein state? Do we know that it is already bigger than the string scale?
It's a very good point. So I'm a bit quick. So whether gravity is completed, UV complete, well, what we know, at least for string theory, but I'm pretty sure it will be for any alternative consistent theory of quantum gravity, is that UV complete gravity not with one particle, but with an infinite set of particles, right? And in string theory, that nicely combines into this infinite set of particles that just combine into a single string with different vibration modes. And indeed, there are typically two towers of particles that arise in string theory. One is all the vibration modes of the string, and the other one is the fact that there are extra dimensions and the vibrations of these extra dimensions themselves, right? And indeed, depending on the vacuum state you are in, the first tower you will encounter in an experiment is these string fluctuations, or the first tower is the vibrations of the extra dimension, right? And to answer your question, so both are possible. I fully agree. But if we want to do reliable computations in string theory, we have to put ourselves in a corner of the theory, not a full theory. And in that corner, it will be the Kaluza-Klein excitations that you will see the first. So it's not a necessity. It's more a restriction because we want to do calculations where we can trust them.
So basically at the boundary of the moduli space, so to speak.
Well, if I don't want to be at exactly. Absolutely. We're at the boundary of what moduli space, which I will explain now. But I just want to mention, it's a fair point that actually one good criticism of string theory, I would say, is that we can only compute with it in specific corners. This corner I call boundary of string moduli space. But I would say it's not a thing of the theory. It's more a problem of humans. It's not a problem of the theory, right? So it's something else. But indeed, it's a good point. So what I've been sort of using, and also in my lecture notes, so this is how you can get away with not knowing string theory, is that we know that string theory reduces to a theory of point particles if the string length is very small. And that theory of point particles becomes a theory of 10-dimensional supergravity, right? And not only is it important that you're in the limit of point particles, that's item number 2 here. Another thing that's important if you want to reduce at least to classical point particles, the coupling constant of string theory, which is a constant that tells you how string diagrams contribute, that coupling constant has to be perturbatively small. So obviously it doesn't have to be. You can live in a vacuum where this coupling constant is order 1 or big. I'm just saying, imagine we choose a vacuum where it's small. We can amazingly use classical 9-dimensional supergravity. to compute vacuum energy. Okay, so that's something a quantum field theorist could never ever have told you or guessed. That the power of string theory calculations is that we can sometimes compute a classical vacuum energy, and it's actually very close to the full quantum result. Okay, so that I think is the magic, and that's where most of the calculations of string theorists are done. And of course, it's crucial that in string theory we go beyond, and many people do. I will just tell you what we know for not going beyond this limit. Okay.
Can I ask something again?
Yes. Yes.
We know that this G string depends on some moduli field, right?
Yeah.
Do we need the equation of, do we need any vacuum? I mean, we need a vacuum to compute G string, right?
Yes.
How do we know beforehand that we have a supergravity description?
It's an excellent question. So what usually happens is that you make a suggestion for how the vacuum looks like. You say, okay, I'm going to look for a vacuum with small gs and say large dimensions so that the point particle approximation is valid. Then I do the computation in that regime. And then I can read off the value of the moduli. And if they don't obey my assumption, I have to throw away my solution. So it's always a self-consistency argument that you have to use. Exactly. Yeah. So what I was just saying that indeed, there's one number that you have to read off in the vacuum. So in string theory, there don't exist any couplings. Everything is a result of a calculation. So if I assume I'm in the limit where I can trust standard supergravity, then I'm in this corner, which means that the string coupling has to be very small and the point particle approximation has to be correct. And I wrote this symbolically by saying that the volume of the extra dimensions has to be large enough in string units, okay? It's just one way of saying it. And so then the theory is just 10-dimensional supergravity. What is it? It's your Einstein gravity as you know it, so Einstein-Hilbert. And then with some extra fields, there is a scalar, which we call dilaton. And that scalar determines the string coupling, GS, as e to the phi, okay? And then there are a bunch of fields which we call fluxes. They're just generalizations of Maxwell field. So Maxwell field is F nu nu, it has two indices. In string theory, you have objects with all possible indices up to 10. Okay? And I think that makes a lot of sense. In fact, it's also true in 4 dimensions. We think of the Maxwell field, which has two indices. But we also talk of, say, a field strength with 3 indices in physics or 1 index. These are called axions, and they're also contemplated. Yeah. Okay, so a little bit more. The point I want to make is that many people write complicated papers with a lot of fancy mathematics about, you know, what we call flux compactifications. But honestly, the physics involved is very easy. You can explain it to, you know, bachelor students without a problem, at least at the intuitive level. But the intuitive level, I think, captures all of the essential physics. So if you want to calculate vacuum energy, there are mainly 3 contributions in this corner of string theory. There is a curvature of the extra dimensions, which I will explain first. That is what we call branes, and then there are these fluxes, and all of them contribute to the vacuum energy. So how do curved extra dimensions contribute, right? So the only thing you need to do is you take the Einstein-Hilbert term, and it tells you that it roughly splits into a 4-dimensional Einstein-Hilbert term, which gives you 4D gravity. And then there's the 6-dimensional Einstein-Hilbert term. But, you know, this, how does it appear? This, you integrate over it, so it appears in the action as a potential energy, right? So this is minus the potential energy, this term with R6 here. So what you learn is that a positively curved internal dimension, so where this R6 is positive, remember, this should be minus scalar potential, right? So in mostly plus conventions, Einstein-Hilbert action is R4 minus lambda, with lambda vacuum energy. So this term is minus vacuum energy. So positively curved internal dimensions contribute negatively, and negatively curved internal dimensions contribute positively to the vacuum energy. So what does this mean intuitively? That if you have a positively curved internal dimension, what does it energetically want to do? It wants to lower energy. Well, it contributes negative energy, so it wants to contribute even more negative. How can that happen? So imagine I have a sphere as extra dimensions. If that sphere collapses to 0 size, then the curvature blows up to infinity, so it starts contributing minus infinity. So that just means that if I have a sphere in gravity, a sphere wants to collapse under its own weight. I think that's sort of an intuitive picture we can all use. Whereas if I have hyperbolic, compact hyperbolic extra dimensions, they want to explode, right? So these are two forces. And so clearly, if I don't do anything else, curved extra dimensions don't give me a vacuum, because either they will collapse or they will explode to infinite size, right? So we need to do something else. And what is that something else? Well, one of the things we do is that we put magnetic fields in these extra dimensions, because you would literally not observe it, and it would give you a consistent vacuum. So these magnetic fields, I told you, it's like Maxwell's equations, but it's with a higher dimensional generalization with more indices, right? So imagine I have 6 extra dimensions. I can, for instance, fill it with a flux that has 6 indices. And what's the physics of that? It's very similar. You can just read it off from the action, so the generalization of the Maxwell action. And you just see that the indices here are contracted with the internal metric, but it's all Euclidean, right? So, and then it comes with an overall minus sign. So that means in general, it contributes as positive energy, right? So what do you want with positive energy? You want to lower it. So how can fluxes lower their energy? By making the extra dimensions expand. It's a little bit like if you have in normal physics, if you have magnetic field lines and you squeeze them together, it will cost you energy. So normally magnetic field lines, they want to expand, right? The system wants to relax. So now this already gives you a flavor how to build a vacuum, right? So one simple example, I can intuitively immediately contemplate. I have extra dimensions, which are a sphere. That sphere wants to collapse under its own weight, but now I fill it with fluxes, who wants to expand the sphere, and these two forces can find a balance. That's the easiest way to find a vacuum, and these vacua are known as Freund-Rubin. And it turns out that they're all of the form anti-de Sitter space times a compact manifold. And so it turns out that the negative energy of the collapsing sphere is bigger than the positive energy of the fluxes, and that's why you get an anti-de Sitter vacuum instead of de Sitter. Okay. Finally, another
Can I ask
ingredient is
something?
string. Yes, please.
So
Yeah.
when we add the p-form gauge fields, there are new p-form symmetries arising in the theory. Do they contribute anything interesting to the story?
Yeah, they contribute brains. So that's what I wanted
Okay.
to say now. So it's a very good point. So, well, these n-form symmetries, they couple to higher dimensional objects which are charged under these higher form symmetries, and that we call the brains of string theory. Exactly, it's a good point. So string theory is not just a theory of strings, which makes sense. So what string theory, the main message of string theory is telling us that normal quantum field theory is based on point particles, but why? I mean, why would nature just restrict to point particles? And string theory is telling us, no, the main message of the theory is just that anything is possible. You can have points, you can have lines, you can have surfaces, right? And these we call brains. And the crucial thing for us is that a brain has a certain tension. And And what you can do, if you want to build a vacuum, you can take one of these brains and, imagine, just let me give an example. You take a brain which has 3 dimensions and time. We call that a 3 brain. And imagine I wrap that 3 brain over 3 compact dimensions. So how will it appear to me for the observer? It will appear as a point. But the point is heavy, it's like a black hole. It gravitates into a black hole. So that's not what I call a vacuum. A vacuum should not have any black holes. It should have nothing, right? So how do you build a vacuum? We're using brains. Well, the brains have to fill the entire universe, right? Because then you just live inside that brain and you wouldn't see it. And so what you do to take a brane, you take a brane which at least has 3 dimensions. And then the remaining dimensions of the brane are wrapped around the compact dimensions. And then it's just rubber sheet physics, right? If the brane has positive tension and you wrap it around those dimensions, it's just like an elastic band. It wants to, contract those dimensions. So it gives you an extra force on top of the flux force and on top of the curvature of these extra dimensions, right? And so what is the game to play? The game to play in the classical corner of string theory, which I explain in my lecture notes, is that, you just add those two forces. So there's the magnetic fields, there's the branes and the curvature. And then you plot or you compute the way the energy depends on I don't know, here I given a field. This can be the dilaton. This can be the size of one of these extra dimensions. It can be anything. But you want to have a vacuum, right? And so the thing we have established in string theory for sure is that there are many stable or metastable anti-de Sitter vacua with negative energy. Metastable de Sitter has been very difficult and is still being debated at this point. Okay, and so once you find a vacuum, to make sure you did the calculation correct, you need to make sure that the stabilized field values are consistent with your approximations, which was point particle and small string coupling. That's a game to play. Yeah, so let me skip this slide. I just want to add one more thing, which is very difficult to explain, and I've made an effort also in the appendix of my lecture notes. The bizarre thing of string theory, it gives us branes with negative tension, right? So normally in quantum field theory or ordinary field theory or even mechanics, you would say that negative mass objects are inconsistent. And that is to a large extent correct. But the way string theory gets away with having them, and by the way, they're called orientifolds, is that you cannot produce those guys like that. So those negative tension objects in string theory, they come only with specific multitudes. Like you can only have, say, one of them. Whereas if a theory allows negative mass particles, what would happen is that the vacuum would become unstable because you can just produce an arbitrary number of them. String theory solves that problem by having very specific negative mass objects, but you cannot produce them just like that. They're fixed by a certain topological condition. Anyhow, just remember they're negative tension objects. They're called orientifolds, and they will be crucial for what I'm going to explain you in the last part of the talk. Okay. And so the last part of the talk, I finally want to address the cosmic hierarchy problem. So what have I been telling you? I've tried to argue in the first part that extra dimensions play a natural role in string theory, and that they're, I think, a very healthy sign that a theory has extra dimensions. I then explained what is the cosmic hierarchy problem, and then I explained to you that the amazing thing is that the physics of extra dimensions in string theory tells you directly what is a vacuum energy. So there's a strong relation between vacuum energy and extra dimensional physics. And now I want to discuss whether we can actually solve the hierarchy problem. Is this physics of extra dimensions telling you that the vacuum energy can be ridiculously small? Yes or not? Okay, let's check it out. So as you just told you, we all agree that it's easy to find anti-de Sitter vacua instead of de Sitter vacua, and I'm just going to focus on them. I understand that we all believe that the observable universe has rather positive than negative dark energy. But, I first want to solve simple problems instead of solving everything. So we always, like anything in physics, we cut the problem into pieces and we try to solve each piece and then put it all together. So at this point, I want to ignore positive vacuum energy and I want to solve the hierarchy problem for negative energy universes, okay? Because also that we cannot. Good. And so I want to remind you of the definition of naturalness in effective field theory. And the definition of naturalness is telling us that if we don't fine-tune, then the size of vacuum energy should be the scale of new physics. That's what quantum field theorists will tell you. And I told you that if there are extra dimensions, the scale of new physics is what we call the Kaluza-Klein scale. And what is amazing is that this is correct. So in string theory, we can compute it. And maybe you guys are familiar with some of these vacua, the most famous being ADS5 cross S5, which has been first used for holography. Indeed, what do we see in ADS5 cross S5? We see that the energy scale, which I called m lambda, or the mass scale associated with the cosmological constant, is of exactly the same order as what we call the Kaluza-Klein scale. And you know this, right? Because it's just a statement that in ADS5 cross S5, the curvature scale of ADS5 is the same as the curvature scale of the S5. So if you put an observer in that guy would say, no, this is not a 5-dimensional universe. This is a 10-dimensional universe, right? So in that sense, the word ADS-CFT is very problematic. We've never observed something like ADS-CFT. We do not know that that exists. The only thing we have seen so far is that when there are CFTs, which have emergent bulks, the emergent bulk is always 10 or 11 dimensional, okay? And so the point I want to make is that if a quantum field theory says, okay, let's have a natural solution, and if you're in a theory with more than 4 dimensions, then a natural vacuum is the same as a vacuum which is not looking 4-dimensional. And I know this is a trivial thing to say, but it's super deep if you think about it properly, right? Why? And I'm amazed how this is glossed over in the literature. Weinberg explains us there is something called a hierarchy problem, a cosmological constant problem. Fine. But Weinberg assumed 4 dimensions of space-time. Okay? Then I think of string theory, which is at least a toy model that allows me to compute vacuum energy. And I learned that a vacuum, which is natural according to, say, the definition of Steven Weinberg, is not 4-dimensional. So I'm not allowed to even use the language of 4-dimensional quantum field theory. Do you see the problem? So if I need to enforce that I can use 4-dimensional quantum field theory, because that's the framework where we define the notion of cosmic hierarchy problem, then the extra dimensions have to be very small. And the Kaluza-Klein scale has to be very high. So you see there is a circle. I am only allowed to use 4-dimensional quantum field theory on the condition that there is a cosmic hierarchy problem. And I think this is the way string theory goes about this. And I think it's a super elegant way out. And for some reason, very few authors explain it this way. Okay, so what I just said, I hope it resonates, is that 4D quantum field theory naturalness arguments predict a large cosmological constant, but 4D quantum field theory is only valid when I don't have a large cosmological constant, at least in the context of extra dimensions, right? So I think string theory sheds a completely orthogonal light on the cosmic hierarchy problem. Okay, so let us now contemplate whether we can actually have solutions with a small cosmological constant, which means that the size of the observable universe, which I called sort of loosely speaking Hubble scale, is much, much bigger than the Kaluza-Klein length scale. Or in terms of masses, that the cosmological constant mass scale is much, much smaller than the Kaluza-Klein mass scale. So is this possible? Yes or no? That's a big question to ask. And there are some nogos in this corner of string theory. And so there are 2 nogos that I know of. One is based on entropy considerations. So in that sense, it's very heuristic and fluffy. And the other is from the equations of motion, so from the dynamics. And I quickly will explain both of them to you. And I think this part has some overlap with Nicolo's talk. But maybe by hearing something twice, it's easier to understand, okay? So I will now run through both of these arguments, but I will do it very quickly, yeah? So, and they're non-trivial arguments. So I'm going to flash them very fast. And I'm going to pretend they're easy. They're not easy at all. I'm going to be honest. Even I have a very hard time understanding the heuristics behind it. So as always with heuristic arguments, they're highly non-trivial, and you need to really, meditate over it to make sure you trust them and you even think they make sense. So I'm not going to do that, but we can always have a discussion about it. So the two famous entropy bounds are called covariant entropy bounds. That's for sure, I would say, the literature would say this has to be correct. And then a more crazy one is called the CKN bound due to Cohen, Kaplan, and Nelson. And I think it has been nicely reviewed in the paper by Castellano, Herraiz, and Ibanez in 2023. So I can write both of these bounds in one formula. That's what they did. It was nice to explain. So I have a quantum field theory. It has a UV cutoff, which I call lambda UV. Don't confuse it with lambda from the cosmological constant, okay? And it also has an IR cutoff. Let me call it lambda IR. And when I couple it to gravity, there's also an M Planck, right? And so what are these entropy bounds telling us? Is that the difference between the ratio between these two extreme scales is bounded by how much the Planck mass difference is bigger than the UV scale. And this depends on the dimension I'm in, okay? And so the weakest bound is with gamma equal 1. And the strongest bound is with gamma equal 2. That is the CKN bound. So let me quickly remind you where these bounds come from. So the covariant entropy bound is a field theoretic bound. It tells you that, okay, in a given region of space, a quantum field has a certain amount of entropy, and it should not exceed the black hole entropy that I can put in the same amount of space. Okay? And if you write out what that implies, you eventually end up with an inequality like this. So it's just like a rough estimate. I have a quantum field. It has an IR cutoff. It has a UV cutoff. What is the degrees of freedom in that quantum field? That gives me a certain entropy. And then you say, okay, that entropy should not overshoot the Schwarzschild radius entropy, and then you get to this inequality. Okay. Of course, the proper Busso bound is much more involved, and I invite you to look at it. There are whole lecture notes written on how to think of the Busso bound, and I'm definitely not the expert. Okay. And then what is CKN doing? CKN is asking a little bit more. CKN says, which of these quantum states are really going to challenge the use of effective field theory? Well, they say those quantum states for which the energy density is maximal, right? And so they contemplate those energy states and they say, well, so I have a state of energy density, the UV scale, and let me assume it fills the whole box, yeah? And then what they're asking is that such a state has a Schwarzschild radius that can fit inside the box. And they're asking that because, if it cannot fit inside the box, then the theory cannot even describe those black holes. So somehow they think, a theory should self-consistently be able to do that. Okay? And this is, of course, super heuristic. You don't know why it should be true. Anyhow, if you do the calculation, I wrote it out here, and you fill it in, you exactly get this relation with gamma equal to 2. Yeah? All right.
Can I ask something?
Yes, of course.
Is there a relation between this lambda UV and the species scale?
Yes, I will get to that right now. Thank you for the question. Yeah, it's a very good question. So indeed, it's non-obvious. Like, what do you mean with cutoff scale? What do you mean with IR scale? These are non-trivial questions to ask, and that's usually where all the discussion is when we start applying those bounds. So let me start with the UV scale. So what we now start believing that the proper definition of UV scale in quantum gravity should be what is called a species scale. And the species scale is essentially, it's an argument Youtube Valley who is telling us, like, look, when do we call, when is quantum gravity strongly coupled? Well, it's when you look at graviton diagrams, and they start to contribute, like the series is just not converged. Well, it never converges, but like the graviton loops are just all contributing at the same order. So normally you would think this happens at the Planck scale, but that's not true. What Valley showed is that if you have a theory of many particles, I'm not sure the standard model, is part of that, but you could think about it. And the number of particles or the number of species is n. The effective graviton diagrams are actually weighted by, instead of the Planck mass, it's given by this ratio. You can think of it as sort of a renormalization of the Planck mass. And indeed, the formula of Dvali completely, resonates with all string theory formulas, because in string theory, we clearly know the cutoff scales. We know when GR gets corrected. And to like one example, if you apply this, say, to a string theory scenario with extra dimensions, what are all these extra particle species? Well, these are these Kaluza-Klein modes. And if you just use your formulas of Kaluza-Klein theory, you fill it in, then you find, and this is beautiful, that the species scale is exactly equal to the higher dimensional Planck scale, which is, of course, what it had to be. Because, that means that the higher dimensional gravity theory becomes strongly coupled. So it kind of, the formula of Dvali works beautifully in many circumstances. So let me use that as a UV scale. Then what is IR scale? That's the toughest question, right? And I think this is where you can debate, and I will throw my hands in the air and tell you I cannot stand my ground too much. But what we did, like Ibanez and friends, we took the IR scale to be the scale related to the cosmological constant, right? I think it makes a lot of sense in an expanding universe where the de Sitter scale is also the observable length scale. Like beyond the de Sitter horizon, things move faster than the speed of light and are causally disconnected from you. In ADS, that's totally non-obvious, right? The ADS scale, for instance, one of the things it tells you about the Hawking-Page transition and so on. But we took faith in a recent paper by Niccolò Cribiori and Fotis Farakos, who actually, not even thinking about entropy bounds, just using other principles, found exactly these entropy bounds, the one I give you here, with the IR scale given by the ADS scale in ADS. So for that reason, I'm going to assume that the IR scale, both in de Sitter and anti-de Sitter, is given by this formula here, square root of the cosmological constant. All right. So then I'm done, right? I fix my IR scale, I fix my UV scale, and I can just plug it into these formulas which I have here. And the only thing I'm going to do is I'm going to use a parametrization, which I think is extremely useful due to Lust, Palti, and Vafa in 2019. And they took a parametrization inspired by all the string theory solutions they knew. So in string theory, and in every solution we know, it is true that the Kaluza-Klein scale is always some power of the ADS scale, which I've called Hubble scale. Maybe it's bad language, but for me, Hubble is always the size sort of the universe, right? Of the observable universe. And so what they've done is say, okay, let us invent a number. We call it alpha. So we say that LKK goes like L Hubble to the 2 alpha, right? So let's take the most famous example, alpha equal 1/2. In such a case, LKK is the same as LADS, and that's like ADS 5 cross S5, okay? So if you want scale separation, if you want the universe where the KK's length scale is much, much smaller than the Hubble scale, this number alpha should be smaller than 1/2. And so what am I going to do? I'm going to say that, well, I'm going to take my entropy bounds, and I'm going to say LKK is my inverse UV scale, and L Hubble is my inverse IR scale. And I'm just going to apply the CKN bound and the CEB bound, covariant entropy bound. So what do I get? This was due to Castellano, Herraiz, and Ibanez. Also, you get a formula like this. So you actually find a bound on alpha, okay? And the bound is actually interesting. It points in such a way that alpha cannot be too small. You see, what do we see here? We see little d. Little d is the non-compact dimension. So for us, it should be 4. What is little n? N should be the number of extra dimensions. So if you like, we can do it 6. Okay, it doesn't matter. And gamma was the difference between the covariant entropy bound and the CKN bound. Okay. So what do I want for scale separation? I want alpha to be smaller than 1/2. And so one of the obvious things we observed in our paper, which for some dark reason nobody did it, is that if you plug d equal 4, and you want, at least 2 extra dimensions or more, you find that scale separation is only compatible with the CEB for at least 2 dimensions, or with CKN for at least 3 extra dimensions. And one of the things it, for instance, implies, in case you have heard of it, is that the recent dark dimension scenario violates these bounds. Okay? And you can ask yourself, okay, what does it mean? It can mean that the bound is incorrect. It can mean that the scenario is inconsistent. Or, and that's what we like to say, it means that we need to step away from vacua, namely from dynamical dark energy. So once you have dynamical dark energy, I have to be very careful in using these bounds because I'm not in an equilibrium situation anymore, right? So these are the bounds on alpha that I got from, I told you here that we would do entropy considerations and dynamics, and I just did the entropy considerations, and now I will go to the dynamics. I will try to see whether supergravity forbids scale separation. So whether supergravity wants alpha to be bigger than 1/2. So we saw that entropy considerations allow it, but it's not obvious. You have to do some, you have to be careful. It also gives you a lower bound on alpha, right? So entropy bounds are okay, but they don't like scale separate. They don't like strong scale separation. Let me put it like that. All right. Okay, so the general no-go from the Einstein equations can be found in this paper I quoted before. It's already from 2015. And I just want to give you the flavor because it's such a trivial computation. I mean, you can give it to anybody who knows like basic GR, okay? And so what I'm going to do this in the context of 11-dimensional supergravity. So 11-dimensional supergravity is essentially the Einstein-Hilbert term and one of these flux fields. And this flux field has 4 legs. It's called an F4 flux. And now there's a technical part. In case you don't know it, don't worry. It's actually not complicated, but I invite you to look at my lecture notes. So if you have a field with 4 legs, it can do 2 things. Either it points inside the 4 observable dimensions we see, or the 4 legs point in the 7 extra dimensions, right? These are 2 options. You cannot have 2 legs in the non-compact dimensions and 2 legs outside, because then you don't have a vacuum. It would break the symmetries of a vacuum, all right? So these are the 2 options. And it can do both at the same time. So I can have a 4-form flux that has, at the same time, 4 feet inside our observable dimensions and 4 feet inside the extra dimensions. And so the easiest mathematical formulation to deal with that is to say, okay, I'm going to replace the 4 feet inside the extra dimensions with what we call a 7-form flux. Okay? Sorry, I'm saying it the wrong way. It's the opposite. So I'm going to say it again. What I'm going to do is I'm going to take the 4 fluxes that point inside our 4-dimensional observable universe. I'm going to replace them with something that's mathematically equivalent. We call it the Hodge dual. I'm going to replace it by 7-form flux inside the 7 dimensions. So in this formulation, it's called sometimes a democratic formulation. I now have 2 guys, F4 and F7, but it's easy. I can always say that all of the indices are inside the extra dimensions. And why is that nice? Because then all the squares that you see here, so all the contraction of indices are done with Euclidean metrics. There's no time, right? So if you write down the Einstein equation, what do you see here? You see the Einstein equation with indices in 4 dimensions, but trace over them. So this is a 4-dimensional Ricci scalar. And in the second equation, you see the 7-dimensional Ricci scalar. So what did I do? I took the Einstein equations and I traced them over the extra dimensions, the compact dimensions. And I have these equations from the right-hand side. I mean, honestly, this is an exercise of like 10 minutes, right? And so I can already learn something interesting. So for R4, I only get minus signs in front of quantities that are purely positive. So this is just demonstrating the usual fact that you cannot get de Sitter, but you get anti-de Sitter. Oppositely, we find that the extra dimensions, when you fill them with magnetic fluxes, the back reaction of these fluxes is such that they are always positively curved. Okay? Nice. So I know these 2 facts. And what can I do now? I can say something about scale separation. Why?
Can I
So
ask
let's
something
try
before
to.
that?
Yeah, of course.
So you argued that if we insert two legs of the field to 4 dimensions and then the other two to the 6 dimension, we don't have a vacuum because it costs energy. But if we have,
it's no, that's wrong. Well, it depends on what you call vacuum. I mean, it's a solution, but it would be like a black hole, but it would not be something that has 4-dimensional Poincare symmetries, or the 4-dimensional ADS symmetries, or the 4-dimensional de Sitter symmetries. Because in such a universe, 2 dimensions would be special. Do you see?
But I was going to ask, if we like choose the field to be flat, is that still a problem?
No, that's perfectly possible, but then it has to be pure gauge.
But
so it
what
has
if we
no
assign
effect.
some non-trivial holonomy? Like
that is possible.
declare the
Very
field.
good. Yeah, that is possible if the topology of the 4-dimensional universe is non-trivial. And indeed, yeah, then but sure, that's possible. Yeah, but it would have no effect on the energy momentum. Yeah.
I see.
Yeah.
Okay.
Yeah. Good point. Right. So for me to jump now to scale separation, I just want to make the following observation, and then I think I should conclude because I'm going too slow, is that if I look at the ratio of curvatures, yeah, it's very trivial to find the following inequality. It's like, you can convince yourself very quickly this is a true fact. And so let us analyze that equation. What is that equation telling us? Well, I can always jump from curvature to length scales using what we call curvature radius. Yeah, I guess everybody knows that. So this equation is telling me that the curvature radius of the compact dimensions cannot be parametrically smaller than the curvature radius of the observable universe. That's what that equation is telling me. Now you can ask me, hey, Thomas, is that important? How do you know curvature radius is Kaluza-Klein radius? How do you know that? And I agree. So one way out of this no-go theorem would be that you can decouple curvature radius from Kaluza-Klein radius. And let me, because due to lack of time, let me just mention it. There has been a recent paper by Yao, Collins, Vacua, and more, who said, we don't believe that it's possible for Einstein manifolds. So that's a hugely important mathematical conjecture, which they have, because it's a conjecture, they didn't prove it, but they showed it for a huge amount of examples. And they must have an intuition to believe this has to be true. But this is a crucially, I mean, it's surprising how easy this conjecture is. You can actually explain it to anybody with a basic knowledge of differential geometry. And it's one of these unsolved problems in mathematics, whether this is true. But imagine it's not true. We can immediately give, then we know that simple scale separated vacua exists in string theory, okay? And then I just want to conclude by showing you 3 ways around the no-go theorem, and I will not discuss them because of a lack of time.
You can continue. We don't have any time constraints. If you don't.
Sure. I have a tiny one, but it's, I don't believe people can focus so long. At least I cannot in a talk. So you can always ask me after, okay? So if you go through the calculation, I gave you the supergravity calculation, you see that what is absolutely needed at the supergravity level is negative tension objects, right? So that's one. And indeed, all of the scale separated vacua in the supergravity limit found in the literature crucially rest on these orientifolds, what we call them, okay? And I could give a whole talk about that. I work mostly on those things, and I think they're super fascinating. But people debate their consistency. And I can explain later why. Personally, I'm not worried at all. I think they're all fine. But yeah, we'll see. Another way out is a third bullet, is what I just told you. It's what I call a new mathematical property. Do there exist what we call Einstein manifolds, where at fixed curvature radius, I can take the Kaluza-Klein scale as small as I want. Of course, I just said a word that mathematicians don't know. They don't know what Kaluza-Klein scale is. So I have to replace it with a mathematical word. And a good proxy for a Kaluza-Klein scale is the lowest non-zero eigenvalue of the Laplacian on that space. So the mathematical papers on this topic, they all talk about the Laplacians on those manifolds and their eigenvalues, okay? I mean, there is a crazy amount of literature in mathematics about bounds on eigenvalues of Laplacians.
Was it the Libanovich eigenvalue?
Oh, yeah, for sure. He started, but they're way, like, I think, yeah. There are too many papers and they all scare me. So, but yeah, there's a lot. And then the final thing, and I will just say it. I told you that instead of a vacuum, I can have a solution, a cosmological solution that's rolling, right? So instead of this, I can have the left side where I don't have a vacuum, but a field is rolling down a potential. And the recent paper written with Nicolo and David Andrew, we show that remarkably, the simplest rolling scenarios in string theory are all such that you roll towards scale separation. And we were just baffled by this because it's a trivial calculation, and we believe it's rather profound. Yeah. So it seems that, you know, once you allow dynamics in the sense of not being in a vacuum, scale separation is a generic thing, I would say. All right. So let me conclude. You know, I had way too much. I just also wanted to explain something beautiful mathematical, that the first thing I can actually relate to the third thing, but that's another story. So the conclusion is that multidimensional picture with dynamical extra dimensions, I think, genuinely changes how we think about unification and the cosmic hierarchy problem, and also the early universe, which I even have an appendix about, but I have no time. So thank you very much for listening.
Thank you, Thomas.
It was my pleasure.
Is there any question from the audience?
I have one question. So thanks for the nice talk. I wanted to ask you about S-duality, if you can explain some details. Like you said that orientifold is somehow S-dual to the third point. Like how precisely?
Okay, so let me try to make this as simple as I can. So most of these orientifold solutions with scale separation, they occur in what we call massive type 2A supergravity. So it's type 2A supergravity with what we call the Romans mass parameter. And those theories have the problem that we do not understand how they come from M theory. Okay, so what we did in a paper was to show there also exist solutions. Well, actually, this was known by Dieter Lust and Simpes and collaborators, that actually also exist solutions without Romans mass. The only downside is that they're not on a Calabi-Yau, they're on something called a generalized Calabi-Yau. And the generalized Calabi-Yaus we understand less. Okay, but the generalized Calabi-Yau they used, we actually understand. It's called a nil manifold. Okay, so technical detail, that exists scale separated solutions without Romans mass on nil manifolds. Yeah. And then, oh, I'm raising my hand for a confused reason, but okay, I don't know why that happened. Why am I telling you that? Because you see, once there's no more Romans mass, it is known that we know the S-dual. The S-dual is literally the lift to M theory, right? And so the usual expectation is that orientifold planes, especially orientifold 6 planes, which are the ones we're using, they lift to M theory as purely geometric objects. Okay, so I don't know if you know this, like a 6 brane in string theory, the D6 brane lifts to what we call the Kaluza-Klein monopole. So it's actually what you think is a singular brainy object in higher dimensions is just a smooth geometric solution, right? And orientifolds are similar, right? So orientifolds, they just become pure geometry. And so what I just told you is that a theory with a negative tension object without Romans mass or 6 planes with scale separation lifts to M theory. And then we checked, okay, what stuff is switched on in M theory in that solution? It's only 4-form flux and geometry. So this must be a Freund-Rubin solution. So the lift of these solutions must give you the spaces that, you know, Vafa and friends say cannot exist. So either you conclude that the conjecture of Vafa is wrong, or there's actually something very non-trivial happening when you want to lift that solution. And yeah, I hope people will work on this in the future. I mean, it's a clear sort of geometric problem that needs to be solved. Yeah, and I'm hoping somebody else does it. Otherwise, we want to give it a try. But I think other people are more well equipped to understand this. Yeah.
Thank you.
Are there any other questions? Maybe we can stop the recording and then ask again.